I will begin. So which question do you have a question about? 116 and 117. That is mission 8, or so I gather not everybody could make it today, and so I want you guys to study these problems for for the test. So I posted the solution already, so you can work through them over break. So hopefully you'll be ready. I mean, it's not ideal, but it is what it is. But since you had a question I want to talk about in person, I'm happy to do that. So 116, we have f of x equal to the sine of this particular quadratic, right? And we're asked to find critical numbers and determine intervals of increase, decrease, and include sign charts of the derivative in your solution, right? Okay, so first of all, the derivative is the derivative of the inside function times cosine of that, right? So I'll just go ahead and write down, the derivative of the inside function is 2x. So what I'm trying to say is, I teach you guys the chain rule to write the du dx after, but like in practice, just for the sake of like formatting, it's often helpful to write the derivative of the inside function first, and then cosine of x squared minus 3x plus 2. So all I'm saying is, like, you might write these in the opposite order, like typically, but I just, whatever. Anyway, that's the derivative. Now, there's a context here, right? Which is 0 less than x less than 3, right? And we have to figure out where is that 0, right? And I would say, so there's some well, first of all, let's take a look back at the function as well. What's this function equal to? Well, the function is, I would point out, you can factor inside the sign, right? Right? So that's going to be 0 at 1 and also at 2, for what it's worth, because sine of 0 is 0. Just something. That'll be useful when we graph. Let me just write that down. All right, so let's return to the question of the derivative. Where is that derivative 0? Well, I think one thing everybody can tell me this. 3 halves, right? If I plug in 3 halves, certainly that's a 0, right? We can all get that one. Clearly, f prime of 3 halves is equal to 0, right? From, that. Oh, that doesn't even show up. So the question is, and this is a kind of tough question, right, is, does the cosine of x squared minus 3x plus 2 equal to 0 for some x in the interval 0 to 3? So how do you decide that? So the derivative can be 0 from the first factor being 0. That's 3/2. That's easy. We just use algebra. Plug in 3. Well, yeah, perhaps we should plug in 0 and 3, and that gives us endpoints, right? Like, fine, I'll figure that out. F of 0 is sine of 2. F of 3 is I think it's also sine of 2. It's kind of funny. So, oh, actually, there has to be, well, 3/2 is between 0 and 3, right? And I mean, Rolle's theorem also says that since there has to exist a f prime of c, which is 0 between 0 and 3, we already found one. What remains to be seen is there another? So when is cosine 0 is my question, really. So you have to think back to trigonometry, right? And we know that cosine of theta equals to 0 if and only if what? Theta is equal to like plus or minus pi over 2, or plus or minus 3 pi over 2, right, etc. There's infinitely many thetas which can make cosine of theta 0, right? So the question then becomes, can we solve x squared minus 3x plus 2 equal to plus or minus pi over 2, or plus or minus 3 pi over 2, right? So maybe a better way to say it is, what does x squared minus 3x plus 2, what values does that take over the interval of 0 to 3? So at this point, for me, the best way to figure the answer to that out is simply to graph x squared, y equals to x squared minus 3x plus 2. And that will reveal for me whether or not there's another critical number. But not just the whole thing, right? So this is actually x minus 1, x minus 2, right? Which is, by the way, another way we could look at it is x minus 3/2 squared. And then, so minus 9/4 plus 8/4, so minus 1/4, I believe, altogether. Could be wrong about that. Let me think about that. I just added 9/4, subtract 1/4, I get 8/4. 8/4 is 2. Okay, good. And so that tells me that the vertex of the parabola is where? 3/2 minus 1/4. And that's right in between the x-intercepts, which are at 1 is at 1, the other one's at 2, right? The vertex here, right, and so this thing, and we're looking from 0 to 3. What's the quadratic do at 0? It's at 2, right? And what's it do over at 3? Well, it's symmetric about the axis for the quadratic. So the quadratic that we're looking at, the quadratic we're feeding into the cosine looks like this. So this is 2. So basically, this answers the question. So apparently, x squared minus 3x plus 2, it ranges between minus 0.25 at the vertex, right, up to 2 at its highest point. So then the question is, okay, great. So does that give me any places where the derivative is 0? Right? Are any of these guys in here? Yeah, what's pi over 2 is about 1.57, right? So only that one is of interest. So we simply need to look for we only need to solve x squared minus 3x plus 2 equal to pi over 2. There will be two solutions. Geometrically, you can kind of see them here. So we expect two critical numbers from this quadratic. So there, in fact, are going to be 3, because this is also a critical number at 3/2 from, right, the earlier expression, which didn't. And so that's a quadratic equation. You can solve that, right? And then what you get, I'm not going to, in the interest of answering more than just this question today, because I could easily spend 30 minutes solving this problem. I think that's how long it took me to solve it on my own. You know, just because there's details that have to go through, and they're kind of picky, and you got to be careful. But here's 0, here's 3. There's the critical number at 1.5, which is 3/2. And the other two, if you solve that quadratic, and it's kind of a mess, right? But if you solve the quadratic, you end up getting 0.15 and 2.85. Those are the two. This has solutions 0.15 and 2.85, approximately speaking, okay? So that gives me one here and one there. And here's f prime of x. And now you have all the critical numbers. And so now you can put in pluses and minuses by testing points, right? Like f prime, what's f prime of 0? F prime of 0 is minus 3 cosine of 2. Cosine of 2 positive or negative? Here's cosine, that's pi over 2, which is 1.57. So cosine of 2 is negative. It's like here-ish. Because this is 3 pi over 2, which is, you know, 2 pi, pi, which is 3, is here, right? And that's where minus 1, cosine gives minus 1. So yeah, cosine of 2 is negative, but minus 3 is negative. We get minus a minus. The derivative at 0 is plus. And then I think when you try plugging in points to the others, it flips signs every time. So you get like that. And so we've got, this is going to be a local max. I'll just say max. This is a local min. This max again. And let's see here. The other thing we've learned from analyzing this quadratic, well, we already know this. Sine, sine could also be 0 if sine was plus or minus pi. Sine of plus or minus pi is 0, right? So just because we found zeros at 1 and 2, in principle, we should worry, are there other zeros for this function? Because sine can be 0 when we plug in multiples of pi. But that's not a concern for the interval of consideration because, well, we're only ranging from minus 0.25 to 2. So the only zeros of the function are the places where the sign takes a 0 in. And so that ends up being 1 and 2, right? So that's pretty much all you need to graph this thing. So let's see here. It starts out at sine of 2, and it ends at sine of 2. It's 0 at it's 0 at 1 and at 2, right? It has a minimum at 1.5. And when you plug in 1.5, you get minus a fourth here. So like you're looking at cosine of minus 0.25 times, sine of minus 0.25, which is negative, but it's about minus 0.25 actually. So like that local min is like here-ish. It's got a local max at 0.15. It's got another local max over here at like 2.85. So it looks something like that. But this problem is more tough than some of the other ones because we have to think about what does it take to make sine or cosine 0, right? And so generally that's kind of a tricky thing. This same problem becomes much easier if instead of putting sine as the outside function, we put exponential, right? Because then exponential is never 0, so like it just makes the analysis much easier if you. But anyway, so that's that problem. But I have the, this is the solution I just posted, and it's in Blackboard to look at. Now, what else did you have a question about?
It was on
You said 117. So the bigger picture here is like what we do to find intervals of increase and decrease. We find the derivative and carefully analyze where can the derivative be 0. That tells me where the critical, or undefined. That tells me where the critical numbers are. Then I draw a sign chart, I put my critical numbers, I test points in each thing, and where it's positive, it's increasing, where the derivative is negative, it's decreasing. If I'm also asked about concavity, then I have to calculate the second derivative and look for places where the second derivative is 0. I don't really have a good name for those. I mean, technically speaking, places where the second derivative is 0, those are critical numbers of the derivative function. You could also say this, numbers where the second derivative is 0 are potential inflection points, right? Just like numbers where the derivative is 0 are potential extremal points or extreme points, but not necessarily. I mean, they happen to all be extrema here because the sign flipped from plus to minus and minus to plus. But if you stay plus to plus or minus to minus, the first derivative tests that it's neither a max nor a min. So like, just because the derivative is 0 doesn't mean it's a maximum or a minimum. Just because the second derivative is 0 doesn't force it to be a inflection point either. So for 117, let's see, what did I say?
I think it's almost the same with the 116.
Right. But it's x squared times sine x this time, and I've added concavity into the mix. So so here we had x squared sine of x, so we differentiate. We get 2x sine x plus x squared cosine x by the product rule. And then I'll just go ahead and differentiate again. If I do it this way, then it's 2 sine x plus 2x cosine x plus 2x cosine x minus x squared sine x. I had to do the product rule twice. Well, the reason I had 2 products. This is a product, and that's a product. So this differentiated to give me these 2 terms. This differentiated to give me those 2 terms. Now, I could have avoided that by doing the following algebra step, which is what? This is x times 2 sine x And this one is 2 minus x squared sine of x plus 4x cosine x. So then we're again faced with the harder part. The differentiation is easy, right? So if you have a problem like this on the test, like make sure you do the derivatives and do them correctly. Like that gets you at least partial credit. The part that's harder here is figuring out when is it 0, right? But also be sure to pluck the low-hanging fruit. Like once you factor the x out, it's easy to see, aha, f prime of 0 is clearly 0, right? So 0 is a critical number. Great. But then the question is that it? Is that it? And I think I gave a context here too. I said 0 less than x less than 2 pi, right? Okay, so the question is then, can we solve 2 sine x plus x cosine of x equals to 0 for 0 less than or equal to x less than or equal to 2 pi? Does that equation have any solutions? So the answer is yes, but it's also not nice. This is why at the start of your homework I have a sentence which says, you know, use Desmos or a numerical method for the parts which aren't pretty. This is one of those parts. But let me encourage you guys to look at this a different way. So that equation, right? 2 sine x, so we could rewrite that as, so consider, well, all right, so something useful to know, sine and cosine are never both 0 for the same x. That's something that's at times useful to be aware of. Just seeing if a student had asked me if I was going to be in today. I wanted to see if they were there. Okay, so it's useful to rewrite that equation as basically like sine x over cosine x. I mean, you could just graph y equals to 2 sine x plus x cosine x and look at the graph and see where it crosses 0. You could do that. That's fine. From a graphing calculator or Desmos, you know. But another way you could look at it would be this. Sine x over cosine x is equal to what? It's equal to minus x over 2. Like that equation is equivalent to this. Because if you subtract x cosine x to the other side, divide by cosine, divide by 2, you get that, right? Which is really the equation tangent of x equals to minus x over 2. And to me, it's more interesting to solve this equation than that equation, because this I can visualize why I'm getting the solutions that I'm getting. And because I know what the graph of tangent looks like, right? And so here's like plus or minus pi over 2, and then plus or minus 3 pi over 2, right? And then, of course, beyond this, there is 5 pi over 2 plus or minus, but those are, right? And so tangent looks like this. Right? Y equals to, that's y equals to tangent, right? Y equals to minus x over 2. Looks like that. So I expect, and of course there's another branch of tangent over here. It remains to be seen of these, of these solution points, which ones fall in the domain of consideration, namely 0 to 2 pi. So, I mean, obviously 0, right? But we already got that one from the other piece, so that we don't. But definitely these two are going to fit in there. And like, I can't find those numbers without using a graphing calculator or Desmos. And when I do that, I found out that there's only 3 actually. And the other 2 that I have pictured are actually beyond the, excuse me, 0 to 2 pi, right? I'm drawing too much. So 0 to 2 pi, 0 to 2 pi. Let's see here, what's next? 5 pi over 2, right? Sorry, I've lost track of what I was doing. I did the same thing when I wrote the solution. But actually, this doesn't matter, because that's negative, right? 0 to 2 pi, right? So I can fix this. Like, let me focus. This is the part that we actually care about. And it turns out that we have x equals to 0, x equal to 2.289, and x equal to 5.087, approximately speaking. Those are this one and that one. And so once I have all that, then I can draw the sign chart. Zero, 2 pi, 2.289, 5.087, and you plug in some points, you get plus, plus, you get minus, minus, pluses again. So this is a max, local min, right? Then the other one, I didn't even, this one I just said, okay, well, at this point, by the time I got to the second derivative, I was tired. So I'm like, all right, I'm not going to try to, like, you could solve this for tangent equal to a rational function and like look at it. So what I'm trying to say is, if you look at tangent equal to a rational function, you could see how to do it without technology. It gives you kind of a window as to how many you expect. You could have, well, anyway, long story short, if we use technology and set this equals to 0, it has solutions 0, .52, and 3.99. And so the second derivative, this is the first derivative. The second derivative sign chart it's got zeros at 1.52, 3.99, and when you plug in points, you get positive here, negative here, positive here. So it so happens that 1.52 and 3.99 are actually inflection points. See, because it's concave up here, concave down here, concave up here, right? Now, I always ask you guys to write the intervals of increase, decrease, the intervals of inflection, of concavity, so I should probably do that. Like this is increasing on 0 to 2.289 and 5.087, right, to 2 pi. It's decreasing on 2.289 to 5.087. It's concave up on 0 to 1.52 and 3.99 to 2 pi. It's concave down on 1.52 to 3.99. But yeah, to find this problem looks simpler than the first one, but actually you can't solve this problem except using like a numerical method. I was able to solve problem 116 without using graphing calculators. This one does look simpler, but it's actually worse, I would say, from a sort of technical perspective. But anyway, so the graph looks, what does it look like? Well, we've got, oh, also, is this thing 0 anywhere? It's 0 at 0, right? It's also 0 when sine is 0. Is sine 0 anywhere between 0 and 2 pi? So when is sine of... Yeah, sine theta equals to 0 if and only if theta is equal to n pi for n an integer, right? So yeah, pi gives us 0 because pi squared times 0 is 0. And 2 pi is also 0 because sine of 2 pi is 0. So this function has zeros at the endpoints and the midpoint, like that. And let's see here. So that's at like, this is, that's pi. 3 is just, 2.28 is like over here. It's got a max at 2.289, so whatever that is. I'm not trying to make this to scale or anything. So there's like a max there. And it's also got a minimum at 5.087, so it's got like a minimum over here. And this is definitely not to scale. Actually, if you look at the actual graph, since it's proportional to x squared, like my picture probably should be more like this one's pretty small, relatively speaking. And this one is much, much bigger because x is bigger. And then we've got concavity. Where's the, I like to draw vertical lines for concavity just to kind of guide my sketch. So my inflection point is at 1.52. So that's kind of like here-ish. The other one's at 4-ish. Like that. So now I have everything. I know my zeros, right? Here's my target max, my target min, and it's got to change from being concave up to concave down. So, well, it's x squared. It's x squared times sine, so it's nothing too familiar. But it's concave up like this, and then it flips over to being concave down, right? Concave down, hits this, and it flips back to concave up again past that. So the graph looks something like that. Now, of course, to make it more explicit, we could actually plug in the numbers into the min-max, and that would essentially fix the scale of the y-axis, but I'm just being lazy in that sense. I think when I actually checked it in Desmos, it was noticeably, like, you can see that this hump is much, I mean, it's about 5, so like x squared is something like 25 there. And that's probably where the sine is 1. So it's probably, this is like 25-ish. And this is probably where the sine is 1. So in principle, like you'd be like, oh, well, sine is 1 at pi over 2. Sine of pi over 2 is 1, right? And sine of 3 pi over 2 is minus 1. So it would be kind of naive to think that the maxes and the mins have to be at pi over 2 and 3 pi over 2. But the thing is, there's a battle between the fact that sine is biggest there and that x squared is getting bigger as you drift to the right in the graph. And so the fact that, because sine goes up, it gets to 1, and then it starts dropping back down, right? As sine is dropping back down, x squared is ramping up. So those two effects kind of counterbalance and drag the maximum from where you might think it would be at 1.57 all the way over to 2.3 here. And I don't know what is 3 pi over 2 numerically, but this is to the right of 3 pi over 2.
That's
4.71. So, I mean, 2.28 is about 0.6 away from pi over 2. This one is only about 0.3, maybe 0.4. This one's closer to, or is it further? I don't know, anyway. But it's complicated because, yes, sine is 1 makes it big, right? But x squared is bigger the further out you go. So it's complicated where the maximum is, and that's what this equation actually tells us. I mean, that's part of the power of calculus. Like, I don't think you could answer the question, where is x squared sine of x, largest with, oh, hey. I think we're almost done. I'll be out in a minute. Okay. So any other questions? Or?
well, I think I'll take a look at others.
Yeah, I've posted the solution. And the other thing I would say is just, as you look at the solution, I noticed some of my later limit problems aren't quite, like the statement of them is not ideal. In the sense that, let's see here, I'll tell you. Problem 126. Let me just let me make a quick list of my sins in terms of problem statements. So I really should have written, to make 126 make the most sense, I should have written the limit as x goes to 0 from the right of x squared over the natural log of 3x. I didn't have the plus there, and technically speaking, that makes the problem easier, because if the plus is not there, I'm asking you to calculate a double-sided limit of a function which is not defined for negative x, which means you can't even take the limit. So, like, as the problem was stated, a lazy but wise student could just say, limit doesn't exist. That's not a limit point. So there's that one, but I can, and then I think problem, problem 127, I actually meant for you guys to take the limit as x goes to infinity of that expression. That was what was intended. That was what was intended there. The problem, as stated, you can just plug in 0. The answer is log 2 over log 8. it's, it was, so I had, this is what was in the problem, I had 0 there. If that's 0, you can just plug in 0, you get natural log of 2 divided by natural log of 8. But what I had intended there to make the problem interesting was infinity. Then it's, there's something to calculate. And also for problem 128, I meant to put x going to 2 from the right. Well. That one doesn't matter. You can go either way. But okay, so you had a question about one of these or something, or problem 126, or does not? Well, I don't know. Let me work it out. So this goes to infinity, and excuse me, that goes to 0. And this goes to what does natural log of 3x do? Natural log of 3x is x goes to 0 from the right. Notice that natural log of 3x is the natural log of 3 plus the natural log of x. And what's the log of x look like? It's this, right? So the limit as x goes to 0 from the right of log x, or log 3x, is in fact minus infinity. And so what happens if you've got something that's going to 0 and something that's going to a very, very, very large number, 0 over something very, very large, it's just 0. Yeah, this one's just 0. It doesn't even require L'Hopital's rule. I might have meant to put infinity here as well. Like if we made this, if we put this as infinity instead of 0, then it might make a more interesting problem. Because if I put infinity there, then this is going to infinity, that's going to infinity. We can do L'Hopital's rule, type infinity over infinity, and we get limit x goes to infinity of 2x over 3 over 3x, right? Which gives me limit 2x squared. And that is not ambiguous. That diverges. So, yeah. Now, like this one, this is going to infinity, that's going to infinity. We can apply L'Hopital's rule. Type infinity over infinity. So I get derivative of the top gives me 16, or 18 rather, yeah, 18x squared divided by 6x cubed plus 2 divided by 3x squared plus 3 divided by x cubed plus 3x plus 8. And then I'll do some algebra. So I get 18x squared times x cubed plus 3x plus 8 divided by 18, not 18, why did I get 18 there? Oh, because there's an 18, duh. So 3x squared plus 3 times 6x cubed plus 2 and So what we really have is the limit as x goes to infinity of 18x to the fifth plus 54x cubed plus 8 times 18x squared divided by 18x to the fifth plus 6x squared plus 18x cubed plus 6. That's infinity over infinity again, because as x goes to infinity, the numerator and the denominator both go to infinity. Now you could do this one with algebra, or you could just apply L'Hopital's rule 5 times. And after the fifth application of L'Hopital's rule, all of them type infinity over infinity. You'd have 18 times 5 times 4 times 3 times 2 times 1 over 18 times 5 times 4 times 3 times 2 times 1. And so the answer would be 1. But anyway. So I'm sorry, I've made these a couple of these limit problems like uninteresting through a typo. But do, study problem 130. Problem 130 is a better problem, and so forth. But.
So plan to do all that test will be
Oh yes, test 2 covers up through mission 8.
from
Yeah, mission, everything we've done since the first test. But of course, this test also will test, power rule, derivative sine, cosine, cosh, sinh, right? So it covers the tail end of what we did on test 1. Like that's, of course, there again, right? But I'm less focused on I wouldn't foresee a question about definition of derivative. So this test is on actual process of differentiation, log differentiation, implicit differentiation, graphing with calculus, related rates, max min. So I think most people in this class need to take a hard look at the related rates problems because a lot of people kind of skip those related rates. Yeah. From what I saw in the homework. Oh, I should give you back your homework. Oh man, I should have given Taylor back her homework. Curses. Yeah, if she wants, I'll give you hers. But anyway, I think that's it. I'm going to cut the video off here. Have a good break, you guys. Test on Monday after break.